What if your AI could defend itself, learn from its mistakes, and even jailbreak other AIs? Sounds like sci-fi, right? Well, buckle up, because today we're diving deep into the cutting edge of AI research that's making this a reality.
Exactly. We've got a packed agenda exploring some seriously cool stuff. First, we're tackling how to make AI better at understanding the world around it using something called knowledge graphs. Think of it like giving your AI a superpowered encyclopedia.
Then we're moving on to the wild world of image generation and how AI can use a chain of thought, basically thinking step by step to create even more realistic pictures. It's like teaching an AI to paint like Bob Ross, but with code.
Next up, we're getting into some serious self-improvement. We'll explore how AI can learn from its own mistakes without needing human guidance, using something called test-time reinforcement learning. It's like AI leveling up all on its own.
And finally, we're diving headfirst into AI safety and security. We'll be looking at systems that can defend against attacks and prevent information leaks, and even explore how to unlearn harmful concepts. It's all about making sure AI stays on the right side of the force. All right, let's dive into this paper on Knowledge Graph Enhanced Multimodal Entity Linking, or KME. It's all about making computers better at connecting things we see and read about to actual entities in a knowledge base.
So, like if I see a picture of the Eiffel Tower and some text mentioning Paris, this system should be able to link that to the actual Eiffel Tower entity in a database.
Exactly. That's entity linking in a nutshell. Now, multimodal entity linking takes it a step further by using both text and images to make those connections. The problem is, most methods ignore the wealth of information hidden in knowledge graphs.
Knowledge graphs? Are those like those relationship maps that show how different concepts are connected?
Precisely. Think of them as networks of information where entities are nodes, and the relationships between them are edges. These relationships are often expressed as triples, which are subject-predicate-object statements. For example, Eiffel Tower is located in Paris.
Okay, I see. So KGMEL is trying to use these triples to improve entity linking. How does it work?
It's a three-stage process: generation, retrieval, and re-ranking. First, since mentions don't usually come with triples, KGMEL generates them using vision language models, VLMs.
Those are the AI models that can understand both images and text, right?
Spot on. These VLMs look at the text and images associated with a mention and create relevant triples. For example, if we have a picture of a basketball player in the text LeBron James, the VLM might generate triples like LeBron James occupation basketball player.
Got it. So it's filling in the missing knowledge. What happens in the retrieval stage?
Here, KGMEL learns joint representations of mentions and entities combining text, images, and those generated or existing KG triples. It uses contrastive learning to make sure that relevant entities are close to the mention in the embedding space.
Contrastive learning? Is that where you train the model to recognize similar and dissimilar pairs?
You nailed it. The model learns to pull the correct entity closer to the mention while pushing away the incorrect ones. This helps it retrieve a set of candidate entities from the knowledge base.
Okay, so we have a bunch of possible matches. How does KGMEL pick the best one in the re-ranking stage?
This is where it gets clever. KGMEL refines the KG triples of the candidate entities, filtering out the irrelevant ones. Then it uses large language model LLMs to compare the mentions information with the filtered triples of each candidate and pick the best match.
So it's like a final sanity check using the power of LLMs. It sounds like a pretty comprehensive approach. What were the results like?
The experiments showed that KGMEL outperformed existing methods on benchmark datasets. In some cases, it improved accuracy by almost 20%. This really highlights the value of incorporating knowledge graph triples into multimodal entity linking.
That's a significant jump. It seems like those KG triples really do act as a semantic bridge, as the paper puts it, connecting mentions to entities in a more meaningful way.
Exactly. The paper also points out that entities often have way more triples than simple textual descriptions, making them a richer source of information. Plus, triples can help disambiguate entities that might otherwise be indistinguishable based on text alone.
So what are the key takeaways here?
Essentially, KGMEL demonstrates that leveraging knowledge graph triples can significantly enhance multimodal entity linking. By generating triples for mentions, learning joint representations, and re-ranking candidates with LLMs, it achieves state-of-the-art performance. It's a solid step forward in making AI systems better at understanding and connecting the dots between what they see and what they read. All right, let's dive into this paper. Reinforcing image generation with collaborative semantic level and token level code. It's all about improving text-to-image generation using some clever reasoning techniques.
CoT, huh? That's chain of thought, right? We've seen that in language models. How does it apply to images?
Exactly. The authors argue there are two levels of CoT at play. First, there's semantic level CoT, which is basically planning the image before generating it. Think about it like this. If I ask you to picture a cat wearing a hat, you first imagine the cat, the hat, and how they fit together, right? That's semantic level CoT.
Got it. So it's like a mental sketch before the actual drawing. What's the second level?
That's token level CoT. This happens during the image generation itself, specifically when generating the image patch by patch. Each patch is generated based on the previous ones, creating a chain of visual reasoning. It's about maintaining coherence and detail as you build the image.
Okay, so semantic level is the big picture, and token level is the fine details. How do they work together in this model, T2I-R1?
That's where it gets interesting. They use reinforcement learning RL with something called BICOT GRPO to optimize both levels of CoT simultaneously. GRPO, or Group Relative Policy Optimization, is a way to train the model by comparing multiple generated images and rewarding the ones that are better relative to the others in the group.
So the model generates a bunch of images from the same prompt, and then what? How does it know which ones are better?
That's the tricky part. Unlike tasks with clear right or wrong answers, image generation is subjective, so they use an ensemble of vision experts as reward models. These experts are different AI models trained to evaluate images from various angles, things like aesthetic appeal, object detection, and how well the image matches the text prompt.
An ensemble makes sense. One model might be easily fooled, but a group of them should be more robust. What kind of experts are we talking about?
They use a human preference model, HPM, to judge aesthetic quality, an object detector to check if the objects in the prompt are present and in the right place, and a visual question answering, VQA model, to verify object attributes. They also use an output reward model, ORM, to directly assess the alignment between the prompt and the image.
So it's like having art critics, detectives, and fact-checkers all rolled into one. What were the results like?
Pretty impressive. They saw significant improvements on benchmarks like T2I Comp Bench and WISE, even outperforming state-of-the-art models like Flux.1. The model was better at understanding complex prompts, reasoning about user intentions, and handling unusual scenarios.
Give me an example of one of those unusual scenarios where T2I-R1 shines.
Okay, so one prompt was a pig on the bottom of a train. The T2I-R1 model, using semantic level CoT, reasoned that the pig would likely be lying on the bottom of the train, creating a more sensible image. Without that reasoning, the baseline model just produced a confusing mess.
That's a great example of how the semantic level CoT adds a layer of common sense. So what's the takeaway here?
The key is that by explicitly incorporating and coordinating these two levels of CoT, the high-level planning and the low-level detail generation, they've created a system that's not just generating images, but actually reasoning about them. It's a step towards more intelligent and human-aligned image generation.
Definitely sounds like a promising direction. Combining the power of language models with the intricacies of image generation. I'm curious to see where this leads.
So this paper introduces test-time reinforcement learning, or TTRL. It's all about training large language models, or LLMs, using reinforcement learning, but without any labeled data. Think about that, RL without ground truth. How do they pull that off?
That sounds wild. So the big problem is figuring out the reward during inference, right? Because usually RL needs that feedback to learn. How can you tell if the model's doing well if you don't have the right answers?
Exactly. That's where the clever part comes in. They found that techniques already used in test-time scaling, or TTS, like majority voting, can actually give you pretty good rewards for driving the RL training. It's like the model is learning from its own consensus.
Okay, hold on. What's test time scaling? Is that just making the model bigger at test time?
Not exactly bigger, but more computationally intensive. TTS is about enhancing the reasoning of LLMs by throwing more compute at the problem during inference. It can involve things like generating multiple answers and then picking the best one. The paper mentions that TTS can be more efficient than just scaling up the model during pre-training.
Got it. So TTRL uses this majority voting thing to figure out a reward. Can you break that down?
Sure. Basically, the model generates a bunch of candidate answers to a question. Then they use an answer extractor to get the predicted answers from those outputs. Majority voting means they pick the answer that shows up most often. That becomes their estimated label, and they use that to calculate rewards.
So if the model's output matches the majority voted answer, it gets a reward, and if it doesn't, it doesn't.
Precisely. It's a rule-based reward system. The paper even includes some pseudocode for the majority voting reward function. It assigns a reward of 1 if the extracted answer matches the majority answer and 0 otherwise.
That's pretty neat. So what kind of results did they get with TTRL?
Some impressive ones. They tested it on math reasoning benchmarks like AIM 2024, AMC, and Math 500. They used models like Qwen 2.5 Math 7b and Llama 3.1-8b Instruct. On AIM 2024, they saw a performance boost of around 159% with Qwen 2.5 Math 7b, and the average gain across all 3 benchmarks was 84%.
Wow, that's huge. So it's actually learning and improving without any labeled training data. It's like the model is teaching itself.
Exactly. They call it self-evolution, and they found that TTRL scales well. Bigger models tend to benefit more because they can generate more accurate majority voting rewards. But they also noted that models with limited capacity might not see as much improvement.
That makes sense. A smaller model might not have enough knowledge to generate good enough answers for the majority voting to be effective. Did they compare TTRL to other methods?
They compared it to the base models themselves, and also to instruct versions of those models that had undergone large-scale post-training. They even included some leading R10-like models, which are trained extensively using RL. But they do point out that TTRL has a different setup, so it's not a completely fair comparison.
Okay, so it's not apples to apples, but it gives you a sense of how TTRL stacks up. What about generalization? Does it only work on the specific task it's trained on?
That's a great question. They found that TTRL generalizes well beyond the target task. They trained it on one benchmark and then tested it on others, and they saw substantial improvements across the board. This suggests it's not just overfitting to the training data.
That's a key point. Overfitting would be a major concern. So it seems like TTRL is not only effective, but also pretty versatile. What are some of the reasons they think it works so well?
They dive into that in the discussion section. One key thing is that RL can tolerate some reward inaccuracy. The rewards don't have to be perfect, they just need to provide a directional signal for exploration. Also, they point out that more accurate reward models aren't always better teachers. The rewards estimated by the model itself might be more suitable for guiding its learning.
Interesting. So even if the majority voting isn't always spot on, it's still good enough to steer the model in the right direction. What about when TTRL might not work?
They identified a couple of potential issues. One is a lack of prior knowledge on the target task. If the model doesn't have enough existing knowledge to handle the complexity of the data, TTRL might struggle. The other is inappropriate RL hyperparameters. Things like temperature and batch size can significantly impact training stability and success.
So it's not a magic bullet. You still need to have a decent starting point and tune the training process carefully. What's the bottom line here?
The paper concludes that TTRL is a promising approach for training LLMs with RL on unlabeled data. It shows that majority voting can provide effective rewards and that models can actually exceed their own training signal and approach the performance of models trained with labeled data. It's a step towards learning from continuous streams of experience without relying on human annotations. Okay, let's dive into this paper about AegisLLM. It's a really interesting approach to making large language models, or LLMs, safer and more secure.
Sounds good. LLM safety is definitely a hot topic. What's AegisLLM all about?
So the core idea is to use a multi-agent system to defend against attacks and prevent information leaks. Instead of just tweaking the model itself, they've built a system around it with different agents working together.
Like a security team for an LLM. What kind of agents are we talking about?
Exactly. There's an orchestrator that decides where the user's query should go based on whether it seems safe or not. Then you've got a deflector that handles the potentially unsafe stuff, a responder that generates the actual output for safe queries, and an evaluator that checks if the response is safe before it goes out.
That's a pretty neat division of labor. So the orchestrator is like the bouncer at a club deciding who gets in.
Haha, pretty much. If the orchestrator thinks a query is risky, it sends it to the deflector, which might just refuse to answer or give a sanitized response. If it seems safe, it goes to the responder, which is basically the LLM doing its thing.
And the evaluator double-checks the responder, right? Makes sense. So what makes this AegisLLM different from other security measures?
Well, most existing methods focus on training time interventions, meaning they try to make the model safer during the training process. But AegisLLM is a runtime defense, which means it adapts in real time to new threats without needing to retrain the model.
Ah, so it's more flexible and can handle evolving attacks. That's crucial because these attacks are always changing, right?
Precisely. The paper emphasizes that static defenses like filters are easily bypassed by clever attackers, and even fine-tuning or reinforcement learning from human feedback, or RLHF, doesn't always generalize well to new attacks that pop up after deployment.
Okay, so it's adaptive. How does it actually adapt? Is it just a bunch of if-then statements?
Not at all. They use something called automated prompt optimization. Basically, they treat each agent's prompt as something that can be improved over time using techniques like Bayesian optimization. They use a framework called DSPY to do this.
What's that?
DSPy is a really cool toolkit that helps you build LLM pipelines that can self-improve. It lets you define what you want the LLM to do in a declarative way, and then it automatically optimizes the prompts to achieve that goal. It's like automatic differentiation, but for LLM prompts instead of neural networks.
Okay, so DSPy helps them fine-tune the instructions for each agent to make them better at their specific tasks. That's pretty smart. What kind of threats did they test AegisLLM against?
They focused on two main areas, unlearning and jailbreaking. Unlearning is about removing sensitive information from the model, and jailbreaking is about preventing attackers from tricking the model into generating harmful content.
Unlearning is tricky. How do you make an LLM forget something without messing up everything else?
Exactly. They used a benchmark called WMDP, which tests the model's knowledge of things like biosecurity, cybersecurity, and chemistry related to weapons of mass destruction. The goal is to make the model less accurate on those topics while still being good at general knowledge.
And how did AegisLLM do on that?
Really well. They achieved near-perfect unlearning on some of the WMDP subsets, meaning the model was basically guessing on those questions. And importantly, it didn't significantly hurt its performance on general knowledge benchmarks like MMLU and MTBench.
Impressive. So it's like targeted amnesia without brain damage. What about jailbreaking?
For jailbreaking, they used a benchmark called Strong Reject, which tests how well the system resists adversarial attacks. They also used pH tests to measure how often the system falsely refuses to answer harmless questions.
So it's a balance between being secure and still being helpful. How did AegisLLM fare there?
It achieved a significant improvement in jailbreaking resistance compared to the base model, without a big increase in false refusals. In fact, its false refusal rate was lower than many comparable methods.
That's a key point. A security system that's too sensitive is just annoying to use. So AegisLLM is both more secure and more usable. What models did they use for these experiments?
They used recent open-weight models like Llama 3.8b, Qwen 2.572b, and DeepSeek R1. They also did ablation studies to see how much each component of AegisLLM contributed to the overall performance.
Ablation studies are always good to see. What did they find?
The ablation studies showed that prompt optimization was crucial. The optimized system performed significantly better than the unoptimized version, both in terms of unlearning effectiveness and jailbreaking resistance. It really highlights the importance of carefully designing the prompts for each agent.
So it's not just about having the agents, but also about giving them the right instructions. That makes sense. Any other interesting findings?
Yeah, they also showed that AegisLLM can quickly adapt to new attack patterns with limited exposure. By training on just a few examples of new attacks, the system could generalize to defend against a broader range of attacks.
That's a big deal. It means the system can learn and evolve without needing constant retraining. So, what's the takeaway here?
The main takeaway is that AegisLLM offers a promising new approach to LLM security by using a cooperative multi-agent system that adapts in real time. It's a strong alternative to traditional methods that rely on modifying the model itself. It's a shift towards seeing security as an emergent property of coordinated agents, rather than just a feature of the model.
Sounds like a significant step forward in making LLMs safer and more reliable. I'm curious to see how this approach evolves and gets adopted in the real world.
All right, let's dive into this paper. The Dual Power of Interpretable Token Embeddings, Jailbreaking Attacks and Defenses for Diffusion Model Unlearning. It's all about how to make AI forget harmful stuff, but also how easily those forgotten things can be brought back.
Sounds like a digital game of whack-a-mole. So, diffusion models, that's like stable diffusion, right? The thing that makes images from text?
Exactly. And these models can accidentally memorize and reproduce harmful content if you prompt them the wrong way. Think unethical images, copyrighted material, the works. So researchers have been trying to unlearn these harmful concepts by fine-tuning the models.
Okay, makes sense. But the paper says these unlearning methods aren't foolproof?
Big time. They're vulnerable to jailbreaking attacks, where crafty prompts can trick the model into generating the harmful content again. The problem is, we haven't really understood why these unlearned models still remember the bad stuff. That's where this paper comes in.
So what's their approach? How do they make sense of this remembering?
They've developed an attack method that learns interpretable attack token embeddings. Basically, they find a set of special text tokens that, when added to a prompt, reliably trigger the model to generate the harmful content. And the cool part? These tokens can be broken down into human-understandable textual elements.
Whoa, so it's like reverse engineering the model's memory. What did they find when they broke down these tokens?
That even after unlearning, the models retain the target concept through implicit textual components. It's not the obvious words, but more subtle associations that still linger in the model's mind.
Implicit associations. Like if you're trying to unlearn violence, the model might still associate it with words like anger or fight?
Precisely. And these attack tokens are robust, meaning they work across different prompts and even different unlearned models. That's a pretty big deal.
Okay, so they can attack the model in a smart way. But what about the defense part the title mentioned?
Based on their attack insights, they designed a defense method that removes these learned attack token embeddings. It's like surgically removing the harmful associations from the model's vocabulary.
How does that work in practice? Are they just deleting those tokens?
Not exactly deleting. They use something called orthogonal subspace projection. Imagine the model's vocabulary as a big room. The attack tokens live in a specific corner of that room. The defense projects everything away from that corner, effectively neutralizing the attack tokens.
So it's like creating a force field around the harmful concepts? Does it actually work?
The experimental results look promising. Their attack is effective at jailbreaking unlearned models, and their defense significantly reduces the success rate of these attacks. Plus, the defense seems to work against other existing attack methods too.
That's awesome. So what are the key takeaways here?
First, current unlearning methods are vulnerable because they don't fully erase implicit associations. Second, these associations can be exploited to jailbreak the models. And third, by understanding these associations, we can develop more robust defenses.
It sounds like a crucial step towards making AI safer and more reliable. But I guess the cat and mouse game between attackers and defenders will continue?
Absolutely. But this paper provides valuable insights into the mind of diffusion models, giving us a better chance of staying one step ahead. Wow, that was quite the journey. From giving AI encyclopedic knowledge to teaching it to paint and even defend itself, we covered a lot of ground today.
Definitely. It's amazing to see how AI is learning to reason, plan, and even self-improve, all without constant human intervention. That whole idea of AI learning from its own consensus is pretty mind-blowing.
And the progress in AI safety is really encouraging. Building systems that can adapt to new threats and unlearn harmful concepts is crucial for ensuring AI remains a force for good.
It's fascinating how researchers are reverse engineering these models to understand their vulnerabilities and then using those insights to build stronger defenses. That constant push and pull is what drives innovation, right?
Absolutely. It's clear that the field is moving beyond just building powerful models to really understanding how they work, how they can be misused, and how to make them more robust and aligned with human values.
So true. It feels like we're just scratching the surface of what's possible. Who knows what incredible advancements we'll see in the coming years.
Well, whatever comes next, we'll be here to explore it with you. Thanks for joining us on this deep dive into the world of AI.
Until next time, keep exploring, keep questioning, and keep pushing the boundaries of what's possible.